So what I want to talk about today is this notion of how and why we distinguish binary stars from planets. I think if you don't spend a lot of time thinking about either of these issues, it either seems trivial or useless. And I hope to convince you that it is neither. And the reason for that is that if we understand the sort of the population demographics, by which I mean the distribution of mass ratios, separations, orbital properties, compositions of both sort of ranges of companions, both planets, things like Jupiter or Earth, and stars, my hope is that we can use this to provide insight into the different formation channels and understand the basic physics that gives us these different types of systems. And if we understand that physics in these different formation channels, that also allows us to better probe the parts of space that remain observationally hard to reach, even with all the advances we've made in the last few years. And I just want to remind you that these objects, though, again, if you not think about it very, very often, they may seem very dissimilar. They actually span a sort of continuum, both in mass and mass ratio. There's not a sharp break between what we call a star, a brown dwarf, or a planet, right? We usually base those definitions on nuclear physics, whether they burn helium or burn hydrogen, deuterium, or nothing. But that distinction is not necessarily correlated with the physics of how they form. And importantly, they also span a wide range in mass ratio, in metallicity. So stars typically have a metallicity of a few percent, like our sun. The Earth is on the opposite extreme, right? That's got a metallicity of effectively 99%. So that's exactly the opposite. And Jupiter sits in between, both in terms of the mass ratio and in terms of the metallicity. So, right, mass ratios for stars in binaries tend to be, let's say order 0.1 and higher. Earth is like 10 to the minus 6, Jupiter 10 to the minus 3. So I want to start out now with a quick outline of what I want to present to sort of put this in context. I want to give you a brief recap of star and planet formation. I want to show how I think we can move towards a successful model of giant planet formation based on the progress we've made, particularly on the computational side in the last few years. And then I want to spend a little bit of time trying to map these different formation models onto now very well characterized stellar and planetary distributions that have been afforded by the last decade of really large all-sky observational surveys. And I hope at the end of the talk to convince you that maybe we can begin to better understand this boundary between planet and star formation. So I've started the talk by saying star formation, but I'm going to spend the rest of the talk really talking about binary formation. And I'd like to use this plot to demonstrate to you why I think it's fair to call star formation binary formation. So this comes from a recent PP7 review chapter we wrote. This is primary mass on the x-axis and companion frequency on the y-axis. And you can see that there's this sharp increase in the companion frequency as a function of primary mass, with our sun living right here at a companion frequency of about a half, meaning that roughly half of sun-like stars are found in binary systems. For those of you who are paying close attention to this y-axis, but maybe haven't looked at this definition here, the notion that companion frequency can be greater than 1 is often confusing. What does that mean? It simply means that when you're talking about these very massive stars, they not only have most of the time one companion in the system, but 2 or 3. And that's how you get a sort of net companion frequency that's order unity. So it's not just that all O stars are in binaries, the vast majority of them are probably in triples or even quadruples. So multiplicity is everywhere. So how do we actually think that these stars and binaries form? We've tried to break it up into 4 different channels, and the boundaries between these are actually a little bit fuzzy, although at least most of these are no longer sort of spherical cow collapse cartoons. So on the top, you've got the cartoon. The middle panel is a hint at an observation that looks an awful lot like the theoretical model. And at the bottom, you have a representative numerical simulation of the process. So we think on the largest scales and at early times, we have either turbulent filament fragmentation or core fragmentation. And again, the difference between these two things is maybe a little bit size scale, a little bit geometry, but the boundary is quite fuzzy. The basic idea is that you have a turbulent star forming environment where you have, magnetic fields and all these things generating these complicated structures. And out of these structures, you get density perturbations, which become unstable to gravitational collapse. And sometimes these two perturbations are sufficiently close that they're just bound to one another, and they will many times remain bound for the rest of their lives. Some of them obviously do not form bound, and they may be single stars, and other things that start out their lives bound can eventually evolve to be unbound through later time dynamical interactions. If you're a little bit more patient and you wait longer, there's another channel of fragmentation that we think produces binaries on slightly smaller scales, where you first form a disk around one star, it becomes sufficiently massive that it becomes gravitationally unstable, and then a second star can actually form and grow in this disk. And then finally, there's this last mechanism called capture. And I want to emphasize here that when we talk about capture in the context of star formation, you should not be thinking about pure n-body dynamics like you might have in a globular cluster. If you have very high stellar densities, as in a globular cluster, you really can have complex multi-body interactions that take two truly unbound things and result in them becoming a tight bound binary. In the context of star formation, we usually think that gas is a very important player, where the way that these two things get captured is through dynamical friction. So I want to emphasize that binaries do not stay where they are born. So if you look back at this first graphic, you can see we've highlighted scales that are as wide as fractions of a parsec. And I'll show later on that most binaries are much closer in separation. And so with all of these different channels, the binaries migrate through strong interactions with the gas. And we can actually model this interaction pretty well via gas dynamical friction with a relatively simple model where we just calculate basically a dynamical friction force that's related to the ongoing accretion onto the stars and the relative velocity with the background gas. And we can derive a semi-major axis evolution rate. And what we find is that the gas densities are sufficiently high at early times that binaries will lose up to 90% of their orbital energy and angular momentum to the gas, which is a good thing because we observe most binaries to be on smaller scales. This is just an example that is judiciously chosen to work extremely well from these simulations, which are magnetohydrodynamic simulations that include radiation from this paper led by Aaron Lee a few years ago. This is the time in the simulation on the x-axis and the semi-major axis of the binary, which is really just a proxy for the binding energy. And you can see the black curve shows what the two stars are doing in the course of the simulation. And the red curve is that simple model where we're measuring the accretion rate and the relative velocity directly from the simulations. So there's still simulation input into that model, but it should give you a sense that this, again, relatively simple picture of just gas dynamical friction does drive binaries to small scales. Okay, so that's sort of one mechanism. I then want to spend a few minutes just reminding people of when this second mechanism of disk fragmentation might be relevant. So I think people often think about gravitational instability in terms of Toomre's Q parameter, something you probably recall from a galactic dynamics class if you're not working on it actively, as some of the people in this room are right now. But I think there's actually another cute way to arrive at this classic result just by considering the vertical density profile of a disk that is in hydrostatic equilibrium. This goes back to Spitzer in 1942. You can turn this ratio in this cos h squared term around and call this the self-gravitating scale height of the disk. So how thick is the disk? It just depends on the sound speed and the surface density and constants. And you can compare this to the classic result for accretion disks in hydrostatic equilibrium when self-gravity is negligible, right? It's just the ratio of the sound speed to the orbital frequency omega. And if you compare those two ratios, bada bing, bada boom, you get 2 raised Q out. And so what that's telling you is that if the self-gravitating disk scale height, right, becomes comparable to the accretion, the one you get from accretion disk, when those two start to balance, that's when the instability, when self-gravity starts to become important. Now, in the context of protostellar disks, I think it's useful to consider what gravitational instability actually looks like. How does it manifest given the typical properties of the disks that are forming around young stars? One thing we find if you calculate what the typical temperatures are based on the irradiation from central stars, the accretion luminosities, the infall rates, we find that there's sort of two cases you can imagine. One in which the disk is relatively massive and therefore has a relatively large aspect ratio. So it's relatively thick compared to the radius, maybe 0.2, 0.3. And another case where the disk is thin. This is probably much more what you're familiar with if you think about AGN disks, where the aspect ratio is small, maybe 10 to the minus 2. If you look at how the instability manifests in these two different cases, morphologically, it's quite different. In this case, you have these flocculent spirals, well described by high azimuthal mode numbers M. And in the case over on this side, you're typically characterized by low M modes. And it just turns out, again, if you calculate the typical temperatures, sizes, and luminosities associated with star formation, this is more often the regime in which you find yourself. And this matters because the regime in which you find yourself is what dictates the types of objects that typically form from the instability in a protostellar disk. So I think it's useful to think about this in terms of the approach to instability. So if you imagine any physical system that you might encounter, right, and you want to talk about an instability, it doesn't make any sense to talk about that system in an astrophysical context as though I have just placed by hand, as if a magical deity, the system at the brink of instability, right? Systems do not exist at the brink of instability. They don't arrive onto the scene at the brink of instability because nature doesn't like instabilities. If something is unstable, it's going to evolve away from that state very, very quickly. So if I want to imagine how I would make an unstable system, I have to start with the system being stable and I have to move it there by some physical process, right? Otherwise, nature just doesn't work that way, right? When you think about the process of star formation, right, you think about starting with a molecular cloud that is relatively stable and then it evolves to become unstable. In the context of a protostellar disk, you can imagine a star in the center, some disk around it, and it has to be not super strongly self-gravitating at some time, because otherwise the disk couldn't exist. So there's two ways, if you think about, again, the sort of cartoon version of how you get there, that you can make a disk unstable. The simplest way that people often think about this, especially coming from the AGN community, is that you can cool the disk down. So you can start with some thermal pressure, some sound speed at some radius and some surface density, and you can just crank the temperature down. And if you crank the temperature down, this number is going to drop. The disk will become thinner, right? H over R will decrease, and you will approach the instability. The only other knob that you have really is to add mass and raise the surface density. That would be changing sigma, or in this version of the fraction, changing the disk mass. And the question is, which one is the most physical way to do it in the context of a protostellar disk? It turns out that the outer regions of disks, maybe counterintuitively, are mostly heated by irradiation from the star. Even though you're far away from the star, right, the flux falls off like 1 over r squared. And if you ask about another heating mechanism, which would be typically something like the dissipation of accretional energy, like viscous dissipation, that falls off more steeply. And so what that means is that the temperature out here in the disk is set by whatever's going on with the star. And that's relatively constant. You can't just take a star and turn it off. It's pretty easy to turn the stellar luminosity up by, say, dumping more material onto it and increasing the accretion luminosity, but it's really hard to crank it down. And so what that means is that in most cases, the best way to drive a disk unstable is to add mass and raise the surface density. This also typically makes the disk spread to larger radii, which again tends to push this parameter down. And as a result, what that means is that while you're driving a disk unstable, you're doing so by dumping mass onto it at a rapid rate. You have to dump mass onto it faster than it can drain onto the star at the center. And this is the simplest way to understand why it's really easy to make more equal mass objects through gravitational instability than to make very, very extreme mass ratios that look more like planet formation. Because no matter what mass scale you start out at, if a little perturbation begins in this disk while you're dumping material on at a very, very high rate, it's very hard to prevent that thing from growing because it typically has first crack at all that material coming in. And so that's one of the reasons we've argued that this is a really good way to make stars and not such a good way in many cases to make planets. So that's a little bit about star and binary formation. And now I want to think about how planet formation might be distinct, even though both of these things can in principle occur in a protostellar or a protoplanetary disk. And I like to think of this as a way to go between the bottom-up approach or the top-down approach. We're in sort of a corporate environment here, so I thought it was maybe appropriate to start with that graphic, but let me quickly cover it up and show you how this actually relates to star and planet formation. So I like to think of star formation or binary formation as a top-down process where you have a gas cloud or a disk that becomes gravitationally unstable and that collapses. At some point, free fall collapse becomes Kelvin-Helmholtz contraction, and then you get dense enough and nuclear reactions turn on. Planet formation, I'm going to argue, is the opposite. It's really a bottom-up process where you start with tiny dust grains that grow into planetesimals. These can collide to make rocky planets, and then some of these grow to be gas giants. And you actually start to cross over between these two, where at some point you do actually come back to a regime where Kelvin-Helmholtz collapse becomes quite important. But again, they have a sort of a different directionality here. So before we get back to the details of planet formation, I want to just remind everybody of where planets form. So I'm sure even the galactic folks have seen this image from the D-Sharp survey before, I suspect, maybe many of you. So these are all protoplanetary disks imaged with ALMA. You're looking at the emission from dust grains at millimeter wavelengths. And what I hope should be obvious is that these disks are not well described by a series of simple power laws. They have a lot of substructure and a lot of different types of substructure. There are rings, there are gaps, there are spirals, there are asymmetries. And so we have to keep in mind that this is the environment in which we're forming planets, and exactly what stage of the planet formation process we're looking at remains uncertain at this point in time. So I think it's useful to keep this picture in mind as we think about what are the main challenges in understanding planet formation and comparing our models with observations. So the first thing to keep in mind is that planets form from a really small, at least by mass, component of the disk, right? If you believe my bottom-up picture, which, again, thinking about the metallicity of Earth, which is 99% metals, right? They need to form from that dust component. And the ISM, like our sun, has a gas to dust ratio of 100 to 1. So your building blocks are a trace component of the material. But to confound things, we actually can't see the particles that are at the crucial building block stage. What we're looking at here is the small dust grains, right? Like millimeter sizes and smaller. But if you want to understand something going from microns to millimeters all the way up to rocky planets, you've got this huge dynamic range in which rocks become totally invisible, right? We don't see meter-sized objects. We don't see kilometer-sized objects unless you're in the solar system. We don't see tens of kilometer-sized objects. And no telescope you build is going to fix this, right? Rocks are just not that luminous, right? If you're, if they're in the solar system and they're getting irradiated by the sun, we can see them, but otherwise, all hope is lost. And so you have to have a theoretical model that can take you from these small things to the big things where you're unlikely outside of the solar system, at least, to have a whole lot of observational confirmation. The next thing I want to emphasize is that the interaction between the solids and the gas are quite complicated. And to make matters even worse, planets don't stay where they're born. I'm not going to focus on this one today. I want to instead focus on this issue of solid-gas interaction. So the reason this is so hard is that dust does not trace the mass in the disk. So I've already told you that the stuff that's going to make the planets is like 1% of all the mass in the disk. So that's a bad place to start, right? But on top of that, the dust is not in the exact same places of the mass. It's not just like we're looking at a uniform 1% trace of the hydrogen, right? That would be fine, actually. That would be pretty good from an astrophysics perspective, if that's what we were doing. We'd be better than we're doing with most, galaxy observations where, again, everyone in the universe would like to observe H2 or H, and nature has been cruel and made that very hard to do for a variety of reasons. So, you're left with these other trace elements like, say, CO. And that's, part in 10 to the minus 4. So if the dust just behaved well and stayed with the gas, you'd actually be doing better than much of astrophysics, but it doesn't because they obey different equations of motion. So the gas in a disk, right, you can imagine the orbital velocity of the gas being controlled by both the gravitational pull from the central star, but there's also this pressure gradient term, which acts sort of to work against the pull of gravity. And so that means that gas is typically orbiting at a sub-Keplerian velocity. Dust, on the other hand, because of the densities, right, basically doesn't feel pressure forces. And so it wants to move according to, our favorite Newtonian laws of gravity. And this distinction between these two velocities creates all manner of problems. So just to give you an illustration of what this looks like, this is just a simple 2D simulation with 4 different fluids. So 1 species of gas and 3 different grain sizes ranging from 10 to the minus 2 10 to the minus 2 to 2 in terms of the stopping time for the experts, or you can think of this as like micron to centimeter sizes. On this side, I'm showing the evolution of the gas in response to a Jupiter mass planet. And on this side, I'm showing the evolution of the dust to gas ratio. And what I just want you to notice is that these two things are not the same, right? The dust is not just tracing exactly where the mass is. And so what that means is that when you're looking at these pictures, right, this is showing you where that trace component of the dust is, but it doesn't mean that the gas has that same structure. So we're not seeing substructures in most of the mass of the disk. So one has to be very careful when you interpret these observations. It doesn't mean that there's no gas and no material here. It means that there's no dust there. It could mean that there's no gas there, but it doesn't necessarily mean that. And so anytime we do one of these calculations, we have to keep in mind that distinction. So how do we think planets form? I'm going to start with the classical model, which dates back to the 1980s and 1990s. And I'm guessing so we've got a youngish age distribution in here. How many people took a planet formation class in graduate school? Okay, so if you had taken a planet formation class in graduate school, which you didn't, or even did you even cover it like at all in a class? Yeah, maybe. There's this guy here who wrote a book on it, in case anyone's wondering. You might ask him. This is the picture that you would have gotten in the late 1990s. This is the picture you should have gotten in the late 1990s. Actually, you would have gotten like a very worse picture that's based on our solar system that still persists in many textbooks today, despite the fact that somebody has actually written a book on it now. But okay, basic parts. So dust grains coagulate to sizes larger than the ISM. The ISM is filled with submicron sized dust. You smush it together by, coagulation like dust bunnies under your couch, and you get to sizes that are maybe millimeters, centimeters, or if you were very lucky, a meter. There's then a problem of making things any larger because, a cartoon version of this is that if you take grains of sand or rocks and you throw them at each other, they do not stick to each other very well. That analogy is flawed in the sense that this is happening in a much weaker gravitational environment, but nevertheless, it remains true that rocks are not very good at sticking to each other when you throw them at high velocities. If you took snowballs instead of rocks, you would do a little bit better. If you throw two snowballs at each other, they can sometimes stick, but if you throw them too hard, they will still fragment. And so in the classic model of core accretion, basically there was an invocation of a magical process by which these tiny dust grains turned into planetesimals. And then once you got to planetesimals, you were okay again because these sort of Kuiper belt or asteroid-sized bodies could then grow via gravity-assisted collisions all the way up to the rocky cores that look like terrestrial planets in our solar system. And in some cases, an optional case, which is actually where this sort of the core accretion name comes from, is that if these rocky cores get sufficiently large that they develop a sort of self-gravitating atmosphere, they can actually undergo rapid, often called runaway atmospheric growth, and grow to be Jupiter masses in size and produce sort of like the large ice giants or gas giants in our own solar system. Now, if you had taken a planet formation class or you ever heard somebody give a talk on planet formation at all, you might have heard some of these things. Planet formation is too slow to make Jupiter and Saturn. If people heard, no one has heard. That's a thing. Yeah, somebody, thank you. Thank you. You make me feel not crazy. People say this. Core accretion doesn't work in the outer disk. I see nodding. You've probably heard this. Core accretion predicts that all super Earths should become gas giants. That's a little more technical, but maybe some people have heard this. And that dust and rocks drift into the star much too fast to make planetesimals, much less planets. So there's all manner of reasons why this doesn't work. And so now I want to address how, fortunately, we have made progress in the theory of planet formation since the mid-90s. And I'd say we have good ways to address many of these challenges. The first revolves around understanding really the growth of solids, not by magic, but by considering sort of a size ladder of how things grow. And the basic model we have now is that at some small sizes, you can get particle sticking. This is sort of the dust bunny analogy. But also the same things that I talked about that made those patterns in the disks complicated to understand, the fact that dust and gas move differently and interact with each other in a complex manner, means that the dust grains can actually get settled into thicker layers in the midplane of disks and increase the density. You can get instabilities driven by drag in the radial direction. You can get complex two-fluid streaming instabilities that can directly take sort of centimeter to 10 centimeter size grains and directly create densities high enough to trigger gravitational collapse into objects that are tens or even hundreds of kilometers in size. And that once you have these large bodies that really look an awful lot in terms of their size distribution, like the Kuiper belt objects that we actually can measure in our own solar system, you can then get ahead to this stage where you get pairwise gravitationally focused collisions. So this is sort of one big solution to sort of how we start to get the growth from these very, very small dust grains up to these proper planetesimals. And from there, we have even more improvements that have solved a lot of the challenges we faced. We know that dust grains probably begin to coagulate to sizes larger than the ISM at very, very young ages. This may be in part due to these pressure traps in disks, although the origin of these pressure traps remains unknown. Planetesimals form with a relatively large size distribution via the streaming instability, which again gets over that magic part of the growth phase. And then another really crucial realization is that because this process here relied on taking relatively small dust grains and jumping in size, this process is not entirely efficient. And so what we end up with is a sort of like two-component population of large planetesimal sized bodies and little pebbles. And it turns out that these pebbles actually can accrete very efficiently onto these growing rocky cores. So you have something that looks like maybe a really, really large Kuiper Belt object, maybe something like Pluto. It doesn't just grow by eating other bodies of the same size. It can sweep up these little small things and dramatically increase the time scale, or decrease the time scale, increase the growth rate to become a large, rocky, terrestrial, or even super Earth-like core. And that solves a lot of the timescale problems. And then the last part is actually a little bit counterintuitive. I'm going to spend a little bit more time on this in a minute, but that the planetary cores, which the classic theory argues will just undergo gas accretion and become gas giants, it turns out that this is a little bit more complex in 3 dimensions than the original theory, and it may explain why maybe gas giants are not so abundant after all. I'll just point out that each of these changes sort of addresses some of these problems that I talked about before. The early grain growth can help explain low disk masses. The planetesimal formation plus pebble accretion can both explain the timescale problems of getting a core and also the efficiency problem of turning enough of the solids into planets. And this last one, again, the complexities of the growth of atmospheres may explain the rarities of giant planets. So I want to take the last part of this talk to try to understand a little bit better this last phase of giant planet formation, using taking advantage of some of the big advances we've had recently in computational modeling. So I started with this traditional runaway model going back to the 80s and 90s, where as long as you grow a large enough core, you can just suck up a big gas atmosphere as long as there's enough disk around to do it. When people started breaking away from 1D models and doing 3-dimensional models, we began to see that if you go to scales well inside the Hill radius, this is sort of the region of gravitational influence of a growing planet, you start to see these dramatically different circulation patterns. Instead of material just collapsing in 1D radially, you start to see circulation, you see rotation, and this complicates our picture of when planets begin to grow rapidly and turn from being mostly terrestrial or rocky planets with a small atmosphere to something like Jupiter or Saturn. And so the approach we're taking now is to try to tackle this problem using massively parallel, GPU-accelerated, multi-fluid, non-uniform mesh, orbital advection, radiation hydrodynamic simulations. And I want to give all the credit here to Leonardo Krapp, who's a postdoctoral fellow, a 51 Peg B fellow at Arizona now, who is doing some phenomenal work with sort of this new version of Fargo 3D. This is an example of this really cool non-uniform mesh that he's developed, where you can smoothly transition your resolution from the global large scales in the disk down to very, very small scales within the Hill radius. Even though the highlights here make it look like this is a nested mesh, this is not a nested mesh. The gradient is actually smooth here, and this allows you to do some really cool things. One of the long-standing tricks in the field of planet formation is to take all the advantages of a Eulerian grid code, where you can do a great job resolving shocks, but take care of the timescale problem associated with Keplerian orbital rotation. So a Keplerian disk, right, is by definition a high Mach number flow, because the Keplerian velocity has to be much bigger than the sound speed, or else you wouldn't have a disk, you'd have a sphere. So the problem with high Mach number flows is that it takes you have to do many, many time steps to advance your grid, to advance your solution. Of course, if this flow is Keplerian, it's very, very predictable, and you know what the background velocity is going to be. And so you can play this game where you basically boost into a rotating reference frame, and then you get rid of that large Mach number flow, and you drastically reduce, say, the diffusion of your numerical method. This is one of the reasons why people usually love Lagrangian methods, right? Because you naturally move at the velocity, the mean velocity of your flow. This doesn't work in most traditional non-uniform meshes, but Pablo Benitez Yambay and Leo have really pioneered this new method where we can actually still use this orbital advection trick on a non-uniform mesh. So keep an eye out for a paper on this coming soon. So what do we actually do with this? So I'm just going to show you one sort of fun example of a calculation we've been playing with to try to understand the sort of three-dimensional complex flows as we try to transition from, sort of mostly rocky planets to gas giants. And so this is a global simulation where we're using 12 different fluids, where you have the gas and then 11 different species of dust, and they're coupled to one another. So the dust feels the drag from the gas and back reacts onto the gas. And then what we've done here is to actually measure how the opacity, right? The dust grains are what is, the dust grains are what you see with ALMA. They're also what's setting the heating and cooling of these systems. So we actually use these interactive, these evolving dust species, which are not just painted on, to tell us how the cooling should proceed in these models. And what we can see here is that even inside the Hill sphere of this growing planet, the spiral wakes that are propagating inwards from this global disk are actually stirring up the dust grain and exciting these interesting flows. And when we turn on radiation transfer in these simulations, things begin to change again. So now we're not only tracking how the cooling will change in these models, but we're actually including that as we calculate the cooling from a growing planet. I'll just show you some results from the isothermal case to give you a sense of why, again, modeling all these different dust species independently is so important. What I'm showing here is the dust to gas ratio and the opacity. So sort of this is telling you how optically thick or thin this planetary atmosphere would be relative to what you would get if you had just painted on the dust grains in a uniform mixture. And what you can see is that the dust structure is highly asymmetric in both longitude and latitude, and that the ratio of the actual opacity to what you would derive from a well-mixed distribution can change dramatically. And what this means is that in the context of trying to understand what we used to know from 1D models, we have to be really, really careful because as maybe you've heard from Jan Fay in the case of and Mathieu for stellar models, right? You cannot just naively take 1D models and 3D models and assume they give you the same results. In this case, you can imagine that I might have one ray along which photons will see, an optically thin cooling, and one direction in which the cooling would be optically thick. And you simply cannot map that onto a 1D model because you're trying to mesh these two different regimes. And so if we really want to understand how atmospheres cool and contract to make giant planets, we have to take into account this three-dimensional structure. So just to close the loop a little bit, I want to point out that, I started by saying, we have this big problem where all we see is the dust, but the dust isn't tracing the mass. So what we're now trying to do is use these multi-fluid simulations to actually ask, well, what the dust grain distribution would look like to either something like JWST or ALMA. And what we find is that to get detection at infrared wavelengths requires really high planetary luminosities because we have to penetrate through this very, very large number of visual magnitudes. And we also have to play some funny tricks with respect to how dust grains settle to find ways to explain observations where we tend to not see circumplanetary disk emission at the millimeter wavelengths, but still see bright spots in the infrared. And so we're still working on what kind of models would be consistent with that. I want to be very transparent here and say that while these are synthetic models of what the emission would look like at 4.3 microns or 1.3 millimeters. These have not been convolved with, instrument noise. It looks less good if you do that. And is anyone here into doing observations? Okay, you don't care about ADI. If you happen to care about ADI and post-processing, we can talk about why there's some concerns we might have about using JWST for high contrast imaging. So, okay, but I'm going to skip past that. So I want to go back to where I started talking about, what we mean by a planet, what we mean by a star, and this notion of metallicity. So, I hope I've convinced you in the last few minutes that understanding how dust moves differential to the gas is really important for planet formation, that planet formation is a bottom-up process. And that, again, when we compare stars to planets, they have these really different trends in terms of how metal rich they are. And so the natural question is that, if what I'm telling you is right, we should be able to see the importance of dust and metallicity in the statistics of stars and planets. And we should be able to use these statistics to validate these models. And so the question is, can we do this? So I'm going to walk you through a few of the basic observations, going into a little bit more detail than just that first plot of there are a lot of binaries. So this is some more detailed plots, again, from this review chapter of the semi-major axis distribution of main sequence and pre-main sequence binaries for different, and on the left-hand side, the different colors are showing different masses. And on the right-hand side, the different colors are just indicating different surveys that are all basically FGK stars, although you should be really careful with that interpretation because at this class 0 phase, we actually don't know the masses of the objects very well. But the idea is that if we look at this side of the diagram, we can maybe learn something about the initial conditions of the binary formation process. So we can see, for example, that at early times, these curves up here, we tend to see maybe a bimodal distribution where we have a lot of binary objects at wide separations and maybe some more close separations. And that if you look at the main sequence, which is this black dashed curve here, we have a log normal. And so it looks like, again, there's this potential validation of this notion that there's maybe different length scales on which binaries begin to form, but that they undergo strong migration and smooth out to this field distribution. You can see that at sort of typical like stellar masses and low masses, the distributions are mostly log normal. They maybe evolve a little bit towards log flat, but it's highly mass dependent and it evolves with age. And again, I just want to, point out for the stellar pop people in the room, please try to use these models when you are doing calculations for anything extragalactic or LISA, because it really makes a difference if you change where the binaries are located. And if you take the sort of statistics at face value from some classic observational surveys, you will get the wrong answer. Katie is nodding her head vehemently. Thank you, Katie, for doing it right. You should all talk to her about how to do it right, because it can really matter. I'll let her be the spokesperson. Okay, so that's the sort of lay of the land. The next big thing that's changed in our understanding of binary star statistics in the last few years is the idea that it's actually dramatically environment dependent, at least in some parts of the parameter space. What we now know is that metal poor solar type stars are much more likely to be in close binaries. So this is Fe on H on the x-axis and the bias corrected close binary fraction, so A less than 10 AU. And this is a variety of surveys that all show this same trend, that as you go from solar metallicities to very low metallicity, the binary fraction dramatically increases. And so this should be telling you something about the formation process. And what we've proposed is that this may actually be related to an increase in the frequency of disk fragmentation at low metallicity. So the way I like to think about this is that I argue to you that for the most part, disk fragmentation is controlled by just dumping too much mass onto the disk and making it unstable, because it's hard to cool a disk down. So I lied to you a little bit because there is, of course, another thing that matters, which is whether or not you can cool as you start to contract and collapse. And that is controlled by the optical depth of your disk. And the sweet spot for cooling, as you all know, is optical depths of order unity. And so, if you take a system and you put it around it and you take the typical parameters for star formation at solar metallicity, you'd find that to make a disk close to unstable, it needs to be on the plus side of optical depth unity. It needs to be just a little bit optically thick. If you make it too optically thick, you'll never cool. If you make it too optically thin, you'll never have enough mass to be self-gravitating. So you end up with disks that are around tau equals a few, where you hit the right conditions to undergo instability. What that means is that as you go to lower and lower metallicities, right, you can marginally increase the rate at which you cool by going from optical depths of a few to optical depths of order unity. And so we think what may be going on is that you're just increasing the number of disks that are able to cool efficiently enough to undergo fragmentation by just slightly cranking down the metallicity. On top of that, you have another helpful fact, which is that the molecular clouds which are dumping material onto the disk are actually optically thin. And if you take optically thin gas and you take away a coolant and you make it more optically thin, it actually becomes less efficient at cooling. And so you raise the temperature just a little bit. And if you raise the temperature of the background molecular cloud, you end up driving infall at a higher rate. And so as you lower the metallicity, you basically add mass faster to a disk that can cool more efficiently. And because you're on this funny dividing line between optically thin at large scales and optically thick within the disk, that you're able to achieve this contrast. And there's been some numerical work that validates this, both before an observational confirmation and after. So that's maybe one reason to think that, again, this disk fragmentation process may well be contributing to some of the binaries that we see, certainly not all, but some of them. But what about the planets? So if we look at giant planet hosts, unlike the binary case, right, you can think of giant planets and binaries as two opposite sides of the mass ratio distribution, right? Giant planet hosts are metal rich. This is something that has been well known, since the early 2000s. And it is still true if you look at much better statistics. This is a really nice summary from Pettigrew 2018. And the one thing that has changed in this 15-year time span is that we can now say that this trend of metal-rich host stars is most prevalent for the most massive planets. So if you wanted to just make a measly little super Earth, it turns out it doesn't matter so much if you have a very metal-rich star. But if you want to be efficient enough in the growth of your solids to get to the phase where you can run away and make a gas giant, you need to start with a metal-rich star, or it's much easier if you start with a metal-rich star. And I think this is a reasonable support for this idea that many parts of the planet formation process, the streaming instability, efficient pebble accretion, are facilitated by being in a high metallicity disk. So again, if you look at the core accretion model, right, it's all about the dust. And so we can see how in the statistics, right, the role of dust, of metallicity, is playing a very, very different role. So, I hope this is starting to convince you that we can, again, really see how there's a statistical support for these two different channels operating at the low mass end and the high mass end. And of course, the question is, what happens at the boundaries between stars and planets? Because this is the thing I tried to emphasize at the beginning, is that we have these definitions of stars and planets that, are based on nuclear physics. And, while people aspire for a grand unified theory, I don't think there's a clear reason why the physics of gravitational collapse should know very much about the physics of hydrogen or deuterium burning. So there's no reason why the physics of gravitational collapse that may make stars and relatively massive objects should know that it has to stop making things as soon as it gets to the deuterium burning limit. There's really no reason for that. And similarly, this bottom-up process of making planets starting from dust grains doesn't know that if it's too good and too efficient and it hits 13 Jupiter masses, that, oh, well, that's deuterium burning, I can't possibly grow anymore. And so if we look at this boundary, what do we start to see? So this is now looking at sort of the objects in between these sort of massive brown dwarfs down to relatively high mass gas giant planets. And this is the relative occurrence rate, not an absolute occurrence rate. And what we can see here is that there are a lot more super Jupiters, things that are really, really basically Jupiter mass objects at these close separations than brown dwarfs. And if I were to extend this plot out a little bit further, you would start to see an uptick when we go to more and more massive objects. And so we think this is consistent with this idea that if you thought that gravitational instability was sort of dominating in this part of the parameter space, we would expect this curve to be much flatter, shifted to these larger masses, because it's easier to make slightly more massive objects. Whereas if core accretion is mostly dominating these sort of this tail of the distribution, we would expect this much steeper fall off in mass ratio. So the last thing I want to do is actually combine the power of these two types of statistics. This is the statistics of binary companions with the statistics of planetary companions. And I think it's useful to think about triple star systems at two different mass ranges. So think of two different types of three-body systems, one in which you have three stars and one in which you have three bodies, but one of those bodies happens to be low enough in mass to call it a planet. So it turns out that they look very different. So the first thing you need to know is that planets overall, not accounting for mass dependence here, don't like to be in close binaries. So if I have a binary that's separated by 1, 10, 100 AU, this is how much suppressed the planet occurrence rate is. So if I have a 10 AU binary, I have a 90% lower, or 90% lower chance of finding a binary in that system as compared to around a single star. So planets don't like to be in close binaries. By the time I get out to 100 AU, basically it seems that planets don't really care if there's a binary much beyond 100 AU. So planets don't like to be in triple systems where there's a close-in companion. On the other hand, close binaries are very often in triple star systems. So this is now going back to the multiplicity fraction as a function of primary mass. This is basically what I showed you at the start. And this curve down here is the fraction of these objects that are actually in triples or higher order multiples. So you can see that many of them are triples. But if I were to restrict this to only close companions and say, if I look at binaries that have separations of maybe a few AU, or not a few AU, a few days, maybe 10 days, 90% of them or more have a tertiary companion. So if I have three bodies and all of them are stars, the close binary really wants to have a tertiary companion. If I have three objects and one of them is a planet, no, it does not want it. It does not like that configuration. That configuration is very rare. So now what if I look at these boundary cases again? I'm now looking at the mass of that very close secondary, where this is a Jupiter mass down here, and these are stars up here. You can see that there's this big jump. And so if I look at low mass objects, right, there's basically a preference against having a tertiary. So having a Jupiter does not make you more likely to have a tertiary companion that's a star. If the object in question is more like a star, say 100 Jupiter masses, then I'm much more likely to have a tertiary system. So you can see that the statistics of, say, 100 Jupiter mass objects look very much like the triple stars that are from this Tocqueville et al. Paper, where again, this is where this 90% figure I just quoted comes from. So if the three bodies are, more like stellar masses up here, then you can go all the way up to whatever mass you want, and it looks, and the demographics match. But when you go down to these Jupiters, you start matching onto the planetary statistics. And to make matters better or worse, depending on how you want to look at it, there's also a metallicity difference here, where the higher mass triple stars, the true triple star systems, have, I know this is still less than a solar mass, this is still higher than the field, lower than the field, these tend to be lower metallicity, and these tend to be higher metallicity. Again, consistent with lower metallicity objects being more often in binaries, and true planets preferring to be in more metal-rich systems. So I think we're, again, starting to see on all these different directions this confirmation from the binary and planetary statistics that we really do have these two different mechanisms that are dominating, but that there is some overlap right in this range at, a few Jupiter masses, because it's just, our boundary is sort of ignorant of the formation process. So I know I'm out of time. I'm just going to leave up the conclusions and take any questions.
Thanks for a cool talk. I have a question about the break in the metallicity dependent binary fraction at 0.1. Is that a like statistically significant break? And can you explain it with the fragmentation argument?
So I mean, this is a very,
do you believe it?
I mean, there's just not that many really low metallicity measurements. The statistics are probably a little bit better with some of Kareem's recent Gaia work. I don't know how low metallicity they go, and I don't think they necessarily see something quite this sharp here. I mean, I could make up a good story for you as to why this is consistent, in the sense that if you drop the metallicity too low and you make disks optically thin, they then become, inefficient at cooling again, and it would suppress the formation of the suppressed disk fragmentation. I mean, I'm telling you a story though. I wouldn't believe that calculation.
Sure. Just a quick question. I'm curious about the Fargo 3D. Like, you say GPU accelerator and mass in parallel. Like, how many GPUs we use to run?
So the cool thing right now is it's not that many GPUs, but the trick is we run different fluids on different GPUs. So each fluid is shipped off to its own GPU, which makes it really easily scalable to do many fluids if that's what you want to do. So that's the way in which it's GPU accelerated. With the current parallelization scheme that is used in Fargo is to parallelize only in the radial coordinate. And so that's a limitation in terms of the ultimate scalability. And one of the reasons for that is that just the communication in the azimuthal direction is hard to parallelize efficiently. With this new non-uniform mesh, I think we could do better maybe, but that's something that we're thinking about in the future. It just deserves more thought, because it would be great to be able to make this scale even better.
And back to the earlier question, when you get to those lower metallicity stars, the ratio of Fe to carbon and oxygen can be quite variable. So I wonder if there's a version of that plot that is in terms of oxygen or something that's really related to the coolant that's related to your model.
Yeah, so I have a lot of slides. I have it, I don't know, I maybe took it out. There's a paper that was led by Dyer with, does not seem to be in here. Okay, I can find it for you later. So we're trying to look at this, right? Which is breaking down, yes, this is 2020. So this is breaking down the close binary fraction as a function of different elements. And it seems like there is a strong correlation with alpha elements. So I tried to get Bruce Drain interested in helping me answer this question, because it is not obvious to me if you should expect the correlation to be stronger with iron or the other alpha elements. I don't know the answer, but it's a good question.
So on the core accretion, I think you see through the population synthesis models, we still underproduce the Neptune size and Earth super Earth, so that's still a big problem. I don't know what's your take on that.
Yeah, I mean, the populations, right? So right now, the way that we solve some of the collapse timescale problems in core accretion is by taking an opacity knob and just turning it down until it starts to look like what we want it to make planets on the right timescale. Right, which is not, I mean, I'm not complaining because then what else are you going to do? Because we don't have a better model. So that one thing that we've been trying to do is use, targeted 3D simulations to come up with a better estimate of like, okay, what should we use as the opacity to get this cooling timescale right? And is there a way we can mock up in a 1D model all the ways in which these 3D circulation flows, really change when you transition from a hydrostatic envelope to the runaway phase, right? So we started with this problem of like, oh, it takes too long to make a gas giant, we shouldn't ever make them. And then we went to like, oh, actually it's really, really efficient. As soon as we start, everything becomes a gas giant. And now we're walking it back a little bit. It's like, actually that only works in 1D, right? And so the problem we have in all of the simulations now is that every time you put in more realistic physics, you basically stop accreting onto these cores. And so we're trying to find, I think there's going to be some combination of 3D flow suppression of accretion and dust settling driven or coagulation driven acceleration of cooling that will hopefully give us the right answer. And I will remain optimistic about that until proven otherwise.